Hello and good afternoon, good morning, good evening, depending on your time zone. Welcome and thank you for joining us today for this media and stakeholder briefing in support of the launch of the Nuclear Innovation Alliance's new report, From Reactors to Repositories, Disposal Pathways for Advanced Nuclear Reactor Waste. Today we'll be joined by NIA staff and special guests for a conversation about this new report and nuclear waste more broadly. My name is Ben Finzel. I'm president of Renew PR in Washington, D.C. I have the pleasure and privilege of supporting NIA on communications, and I'll also be serving as the moderator for today's briefing. Before I introduce NIA Executive Director Judy Greenwald, here's a brief overview of today's agenda. To begin, Judy's going to introduce NIA for those of you who aren't familiar with the Think and Do tank that is NIA. And she'll provide background on why NIA has produced this report and their objectives. From there, I'll come back to introduce NIA Senior Analyst Eric Cothran, who did all of the work to pull this report together. And he's going to give you an overview of the new report. And then Eric's going to be followed by a trio of special guests from the DOE, Oklo, and Columbia University who have joined us today. After their presentations, I'll moderate a live Q&A with all of you who have joined us today for this conversation. As a reminder, you're welcome to start asking questions now if you'd like by typing your name, question, affiliation in the Q&A field. And once we begin the Q&A session at the end of the presentations, I'll do my best to take them in the order in which they're received. But for now, let's get started. And Judy, please tell us a bit about NIA and this report.
Thanks so much, Ben. Welcome, everyone. We appreciate you joining us for this briefing on the release of our new report, From Reactors to Repositories, Disposal Pathways for Advanced Nuclear Reactor Waste. Before we begin, let me tell you a little bit about NIA. We're a nonprofit, nonpartisan think and do tank working to create the conditions for success for advanced nuclear energy to be a key climate and energy security solution. We play a leading role in shaping major legislative efforts to advance reactor licensing, enhance the Nuclear Regulatory Commission's capabilities, and expand and improve the Department of Energy's nuclear innovation initiatives. We also collaborate with a broad group of stakeholders to coordinate advanced reactor advocacy in the United States. As the global demand for clean, firm energy grows, advanced nuclear energy technologies are gaining significant attention, and efforts to deploy them are underway. These advanced reactors offer numerous improvements in safety, efficiency, and operational flexibility, largely due to the innovative fuel forms and coolants utilized in their design. The management of advanced reactor waste will generally look the same as it does for conventional reactors, but with some differences. The specific waste management strategies we use must be tailored to the specific waste being managed. So we're publishing this report and also a summary for policymakers, for those who don't have time to delve into the full report, to provide insights into the characteristics of these new waste streams and how they will be managed. This more detailed understanding should give policymakers and stakeholders the knowledge they need to help create the conditions for success for advanced nuclear energy so that it can be part of the climate and energy security solution. With that, I'll pass it back to Ben.
Thanks, Judy. And I'll point out the report is now live on the NIA website, so you can go to nuclearinnovationalliance.org. You'll find the report there along with the summary for policymakers and a nice little comment summarizing everything from Eric. Now, speaking of Eric, Eric is Senior Analyst for NIA, and he's going to give us a summary of this new report, or at least as much as he can fit into 10 minutes. Eric, good luck, and over to you.
Thanks, Ben, and good afternoon, everyone. I'm very excited to be here today since the release of this report and its summary for policymakers is the culmination of a lot of research and time spent having conversations with key stakeholders who work in this field. I'll go over the report and its key findings in just a minute, but first let me talk about why we wanted to produce this report in the first place. The question, what about the waste, is one we get asked all the time, and it's a good question that those of us who work in the nuclear energy sector need to be able to answer when speaking to policymakers or members of the public so we can gain public trust in nuclear energy more broadly and help ensure concerns about nuclear waste aren't an unnecessary barrier to nuclear reactor deployment. Now, the answer really depends on what classification you're talking about. Low-level waste, including Class A, B, C, and greater than Class C nuclear waste, looks different and is managed differently from high-level waste, which includes spent nuclear fuel. The overall goal of waste management for any of the classifications you see here remains the same, and that's to safely isolate the waste and prevent any release of radioactive material to protect the environment and ensure public health and safety. But the specific storage, transportation, and disposal methods used need to be tailored to the specific waste classification in question. The answer to the question, what about the waste, also depends on if we're talking about waste generated by conventional nuclear reactors or advanced reactors. So let's look at spent nuclear fuel from conventional reactors as an example. We know that it consists of spent fuel assemblies that contain uranium fuel pellets, and that these fuel assemblies have been removed from the reactor core, allowed to cool down, and ultimately have been placed in dry cask storage, like you see here. We know that in the United States, we have an excellent track record of managing the spent nuclear fuel, and in fact, no member of the public has ever been harmed by the spent fuel generated by commercial power reactors. So that covers conventional reactors, but what about the advanced reactors that we are seeking to deploy by the end of the decade? More specifically, what will waste from advanced reactors look like? How will it differ from waste generated by conventional light water reactors? How prepared are we to manage advanced reactor waste streams? And what areas require further investigation? And it's the answer to these questions that are exactly what our new report aims to provide. And just like Judy said earlier, the way we manage advanced reactor waste will generally look the same as it does for conventional reactors. We're going to place the waste in specially engineered containers or casks that are designed to safely store the waste until it has either decayed to a safe level, or for high level waste until we can send it to a permanent disposal facility. But the specific waste management strategies we use must be tailored to the waste that's being managed and its unique characteristics. So in the next few slides, we'll take a closer look at these characteristics to get a better sense of what advanced reactor waste will look like. But before we do that, I should note that the rest of my presentation today will primarily focus on spent nuclear fuel because that's typically what most people are concerned with. And if you want more information on low-level waste, I encourage you to check out the full report. So the characteristics of advanced reactor spent nuclear fuel will vary. More specifically, its physical, chemical, and radiological properties will be based on the reactor technology and the specific company design. The image here shows the spent nuclear fuel generated by 5 different reactor technologies, including advanced light water reactors, high temperature gas reactors, sodium fast reactors, and liquid and solid fueled molten salt reactors. Looking at advanced light water reactors, we'll see that they will produce the same spent nuclear fuel assemblies as conventional reactors. There will be a few minor differences. For example, the overall length of the fuel assemblies used for advanced light water reactors will be smaller to fit in more compact, small modular reactor designs. But overall, advanced light water reactors and their spent nuclear fuel management will be identical to the conventional light water reactor spent fuel management. High temperature gas reactors use TRISO fuel that consists of a uranium fuel kernel surrounded by several layers of carbon-based materials. These TRISO fuel particles are roughly 1 millimeter in diameter, so about the size of a poppy seed. And thousands of these tiny TRISO fuel particles can be embedded into a graphite matrix like the spherical fuel pebble shown here, which is roughly the size of a tennis ball. So in this example, the actual spent fuel is the small TRISO fuel particle, but because there's no efficient or economic way to currently separate out the small TRISO particles from the larger graphite fuel pebble, the entire fuel pebble, including that graphite, is effectively your spent nuclear fuel form, which adds to the total volume of spent nuclear fuel that must be handled and disposed of. Moving on to sodium fast reactors, they will generate a metallic spent nuclear fuel form that has chemically bonded to the sodium found within the fuel rod. And because sodium is highly reactive with water, we have to think about how to design and engineer containers or systems to prevent water from getting inside. This isn't necessarily a large challenge, but it's just an example of the kinds of specific considerations that need to go into managing different spent fuel types. Now, in the interest of time, I'm going to skip over liquid and solid fueled molten salt reactors, but I encourage you all to dive into the full report to learn more about those. Now, moving on to interim storage, because interim storage will play a critical role in the management of spent nuclear fuel, since the United States currently lacks a permanent repository. Fortunately, interim storage strategies are robust, and the United States is well prepared to ensure safe and effective management of spent nuclear fuel, including spent fuel from advanced reactors, until a permanent disposal solution becomes available. This is demonstrated primarily by two things. One, past real-world examples in managing spent fuel from legacy high-temperature gas reactors and sodium fast reactors. We actually first operated these reactors back in the 60s and 70s. So in reality, these advanced reactor technologies and their waste aren't all that new. And number two, advanced reactor developers currently have plans to manage their spent nuclear fuel, which we'll take a look at in a few slides. But first, let's look at number one in more detail. Here, we'll see that the United States has previously operated and decommissioned 2 high-temperature gas reactors and 5 sodium fast reactors, proving that the interim storage strategies we've already developed and used are robust, technically mature, and provide a means to safely store the spent fuel generated by future advanced reactors. So it's really the experience we've gained by already handling and storing these waste in interim storage that gives us a strong foundation for the future management of advanced reactor spent fuel going forward. Here are photos of the sodium bonded spent nuclear fuel from the EBR-2 and Fermi-1 sodium fast reactors, which is currently stored at Idaho National Laboratory. As you'll see, the spent fuel is in dry cask storage just below grade, and everything is stored in a very small footprint. And when I look at images like this, I can't help but think of how similar this looks to dry cask storage of spent nuclear fuel from conventional reactors, albeit below grade instead of above grade. Now, moving away from the legacy reactors and looking towards the current plans that advanced reactor developers have to manage their spent fuel, here is a depiction of X-Energy spent fuel intermediate storage facility that can be co-located with their XE100 high-temperature gas reactor design. In the top left of the image you see here, you can see how spent TRISO fuel pebbles can be moved with the use of a fuel handling system into spent fuel canisters, which can then be transferred to the storage facility through an underground access tunnel. And then the renderings on the bottom here show how natural circulation of air can be used to keep the spent fuel cool. Now, after interim storage, we need to permanently dispose of the spent fuel in some kind of deep geological repository. And while the United States currently has no such repository, it's important to note two things. That is, the safety performance of a geological repository is dominated by the engineered and geological barriers it utilizes, rather than the characteristics of the spent fuel. And therefore, advanced reactor spent nuclear fuel is expected to have little to no impact on the long-term safety performance of geological repositories, provided they are properly processed and packaged before being disposed of. And that begs the question, what does it mean to be properly processed and packaged? Well, some advanced reactor spent fuel may need to be processed prior to permanent disposal to reduce its volume, render it chemically inert, or stabilize it. There are certain challenges that exist, which we must overcome to ensure that some of these processing methods can be used at scale, mainly due to the complexity and current maturity of those methods. But the solutions to these challenges are all known to be technically feasible, and efforts are currently underway to develop them. But not all spent nuclear fuel from advanced reactors needs to be processed. Some of it could also be directly disposed of without processing, and this is known as direct disposal. And the decision to use direct disposal or to process it will ultimately depend on a future repository's waste acceptance criteria. And because we don't have one yet, the exact permanent disposal strategies we need for advanced reactor spent nuclear fuel have yet to be determined. I will note that there's a lot of additional nuance and interesting details that go into this particular topic on processing, which we don't really have time for right now. But those interested should definitely check out the full report to learn more about this or any other topic that's discussed in the report. And with that, I'll turn it back over to Ben.
Wow, well done, Eric. Thank you. That was not an easy task. As a reminder, you can start putting your questions in the Q&A box now if you'd like. Just include your name, affiliation, and question. But first, before we get to those questions, we're going to hear from our 3 special guest speakers, starting with Matt Bowen, who is a research scholar at the Center on Global Energy Policy at Columbia University. Matt will be followed by Everett Redmond, Senior Director at Oklo, And following Matt, we'll hear from Paul Murray. Paul is the Deputy Assistant Secretary for Spent Fuel and High-Level Waste Disposition at the U.S. Department of Energy's Office of Nuclear Energy. I've asked each of our special guests to talk in the order in which I just introduced them so that I won't interrupt the flow of the conversation by popping back and forth to introduce each one again. So I'll come back at the end of their presentations and we'll go right into our live Q&A. But let's get started now with Matt. Over to you.
Yeah, thanks very much, Ben. Next slide. I'm going to provide a very quick overview on the sort of U.S. nuclear policy landscape when it comes to disposal of long-lived radionuclides from spent nuclear fuel. My starting point is 1957, which is when the National Academy of Sciences first endorsed the concept of geologic disposal for high-level radioactive waste. The idea being that there are underground geologic formations that have been stable for very long time periods, longer even than some of the very long half-lives involved in the radionuclides and spent nuclear fuel. And the idea is that a mined repository in these formations could potentially provide a place for the disposal of spent nuclear fuel. You would still have to do analysis to confirm that, as Eric mentioned, the combination of the natural and engineered barriers would sufficiently lengthen the amount of time it would take for the radionuclides to reach the biosphere and protect human health, but that it should be possible, and I think that scientific consensus has endured to this day. Next slide. So, how do we go about getting one of these repositories, since all of the advanced reactor concepts that Eric mentioned will have some level of long-lived radionuclides that will need disposal in one of these facilities? So how do we go about getting one? Well, at least the current policy framework for how that's supposed to happen is still in the Nuclear Waste Policy Act of 1982. We'll talk a little bit later about how the U.S. program isn't really making progress, so we're probably going to need to amend existing law. But the idea was that the executive branch, the federal government, was going to identify 2 locations to potentially host deep geologic repositories for spent nuclear fuel disposal, and these were dates certain. There was even a cap on the first repository until the second repository started operations, which there were some good reasons for having 2 sites, including redundancy. In case something happened to one of the repositories, the other one would still be there. In any case, the idea is that the federal government would take responsibility for disposal, and exchange utilities would pay into a new nuclear waste fund. It was a polluter pays principle. So that would fund the whole program. However, just a few years later, the program suffered a couple of damaging steps. When the Secretary of Energy in 1986 announced that the candidate sites for the first repository had been down selected from 9 to 3, he also announced that DOE was simply deferring the search for a second repository. And this was widely perceived to be under political pressure from states in the East, especially those that had been identified as potential candidates for the second repository. But it did lead to a flurry of legislative activity the next year, with members of Congress introducing bills that would alter the Nuclear Waste Policy Act to, in particular, postpone the second repository program or get rid of it entirely. And what ended up happening is in the conferencing of a funding bill, the conferees named Yucca Mountain in Nevada as the only site that would be characterized for the first repository, which did not go down well in Nevada, where it was promptly dubbed the Screw Nevada Act. Next slide. So obviously the original process that had been laid out in the Nuclear Waste Policy Act did not come to pass. The first 3 candidates for the first repository were supposed to be characterized before the president recommended one to Congress, but Congress amended the Nuclear Waste Policy Act before that happened. There was a cost concern, and I like this quote from Senator Bennett Johnson that I think does a good job of summarizing, some of the cost pressures, but also the political maneuvering that took place. Yucca Mountain was well funded for a good number of years. A lot of science and research was done. 2002, President Bush recommended the site to Congress. As was allowed in the Nuclear Waste Policy Act, the governor of Nevada submitted a notice of disapproval. Congress voted to override that notice of disapproval. DOE would submit an application to the U.S. Nuclear Regulatory Commission to construct Yucca Mountain. That was at the end of the Bush administration. The Obama administration came in and sought to withdraw that application, zeroed out the budget request. Congress has not appropriated money to move Yucca Mountain forward since then. And you had years where utilities were paying over $700 million into the Nuclear Waste Fund, but no money was being appropriated. So eventually, lawsuits led to courts stopping those fees. So we haven't had fees paid into the Nuclear Waste Fund in now over a decade. I won't go into too much more of this, but the Trump administration had reinstated the budget request for Yucca Mountain for the first 3 years, but not the fourth. The Biden administration did not request money for Yucca Mountain. I don't know what the next administration will do. We'll see. Next slide. Apart from this stalemate, I'd argue that there are some reasons, and other people have made these arguments too. We actually do have an operating deep geologic repository in the United States, the Waste Isolation Pilot Plant in New Mexico, which has been disposing of defense-generated transuranic waste for over 25 years, with over 14,000 shipments transported to the site safely. We also, in the 80s, we were not especially concerned about climate change, which has emerged as this imperative where we're extending the lifetime of existing reactors that are today producing 2,000 metric tons of spent nuclear fuel each year. We're talking about building new reactors, which we definitely were not in the late 80s. And on account of all these broken contracts as a result of the failure to take title to the spent nuclear fuel and move the Yucca Mountain project forward, the liability, this is a very recent update, has steadily increased. Now, on the more positive side, other countries have moved forward with their repository programs. Sweden is getting close to construction. Canada just selected a site. Next slide. And Finland, as the sort of international leader, has basically finished building their repository. They're doing this trial run of placing spent fuel canisters in the repository that do not have radioactive material, but they are obviously moving close to that, and maybe disposal operations will start next year or the year after that. Next slide. When the Obama administration moved to withdraw the license application for Yucca, they put together a Blue Ribbon Commission on America's Nuclear Future, which issued reports and recommendations in 2012. I'd say they're still relevant. I don't know, they haven't been implemented since they came out, and I don't know what the new administration or new Congress will do. But the reasoning behind them is in these other countries and with WIP, in the cases where you've had these local communities that have supported the projects, they've been making progress. And in WIP's case, you didn't have the state of New Mexico getting to a point where they opposed the project. As other folks have pointed out, since the 70s, you might want to implement this program outside of Department of Energy, an organization that changes political leadership pretty regularly, and has a mixed track record in terms of engendering trust or mistrust with states and local governments, and fixing the funding to the nuclear waste program would obviously be a good thing to do. As I mentioned, there were years where over $700 million were paid into the Nuclear Waste Fund as mandatory fees, but no dollars were appropriated for the program. And we have not obviously begun an effort to develop new deep geologic disposal facilities. I won't cover the rest of these. I mean, I think these recommendations are still relevant, but we'll see what the new administration and Congress are interested in doing.
Okay. Everett Redmond from Oklo, and thanks to NIA for both the invitation to speak here as well as publishing the report. I think it's a very important part of the conversation to talk about nuclear waste. So let's move on to the next slide. We are a publicly traded company, so have to provide this little heads up in terms of forward-looking statements. Please don't take anything I say as basis for investment. Next slide. I'm going to talk a little bit about our company here in terms of what we do, what the reactor is, and how we're managing waste. Let me start off with what our model is, though. Oklo, we're designing an advanced reactor. I'll touch on that in a second. But we're unique in the sense that we are going to build, own, and operate the reactor. So what we're selling is power, not the reactor, through power purchase agreements. This also means that we, Oklo, is at the end of the day managing our plants as well as our spent fuel. And so that comes into play. It's a different idea than what most advanced reactor companies are doing right now. It makes us actually, in terms of spent fuel, very similar to operating utilities in the sense that we have to manage our spent fuel as well. Next slide, please. So what is our technology? We refer to the reactor as the Aurora powerhouse because, as I said, we are providing power rather than selling the reactor. The first model that we're going to be building is a 15 megawatt electric, liquid sodium cooled fast reactor, uses metallic fuel. I'll show a picture in a second. And it uses high assay low enriched uranium up to 19.75%, or uranium transuranic fuel from recycling, and I'll talk about that as well. It's important to note the HALEU here up to 1975 because that's a big difference from the operating fleet right now, which only uses 5%. So the cost of our fresh fuel, manufactured fresh fuel, and cost of the uranium going into our fresh fuel is going to be noticeably higher than the cost of uranium going into the existing reactors. And that's going to come into play in my conversation. Our next design, though, is going to be a 50 megawatt electric. So we're very quickly going to go from 15 to 50. This first one, 15 megawatt electric, is going to be built at Idaho National Laboratory, and we're going to submit the application to the Nuclear Regulatory Commission for that next year. Next slide. So fast neutrons, why fast reactors? Well, fast neutrons enable us to unlock more energy from the fuel. So basically, you're able to recycle fuel and burn some of the elements, transuranics, that are considered poisons in the water-cooled reactors. So in fast reactors, that poison, if you will, becomes a fuel for us. And so that enables us to do things a little bit differently than the operating fleet. Also, with liquid sodium, you're operating at close to atmospheric pressure, so you're not a highly pressurized system. So more inherent safety is built into the design. Next slide. This has all been proven before. Experimental breeder reactor 2 operated for 30 years at Idaho National Laboratory at what is now called the Materials and Fuels Complex out there. And it demonstrated both recycling, operation of a sodium-cooled reactor, recycling, as well as the inherent safety features of that. They ran some experiments turning off the cooling systems, the reactor heated up and automatically shut itself down based on the physics. Next slide. So let's talk a little bit about deployments for a second. And I've mentioned this already. So the first reactor is going to be deployed at Idaho National Laboratory out there with the license application going in next year. We've also made public announcements that we've signed MOUs with Southern Ohio Diversification Initiative, SODI, in Southern Ohio at the old Piketon facility for the potential deployment of a couple reactors there. We also have letters of intent with a number of companies, and we see the data center area as our potential biggest customer. We have a financial investment from Equinix, one of the larger data center companies out there. And so there's a huge interest, and you've seen in the news recently the huge interest in nuclear from the large hyperscalers as well. So there's a great opportunity here to move forward, and that's what Oklo's doing, as well as trying to appropriately manage the back end of our fuel cycle. Next slide. So what does our fuel look like? So it's metal fuel inside fuel rods. The image you see there is actually a picture of EBR2 fuel. So the metal fuel rods are then bundled together inside a metal can. In that respect, it actually looks very much similar to a boiling water reactor assembly where you've got rods inside a metal can. Ours looks more hexagonal versus square, but still conceptually the same. Uranium, as I said, is enriched up to 19.75%, which is different than the existing fleet. And as I noted, our design is similar to EBR2. So in this respect, we are again dealing with metal fuel, solid fuel, like Eric talked about at the beginning of the presentation. Next slide. Fuel fabrication. So Oklo is going to be doing fabricating its first core out at Idaho National Laboratory at the Materials and Fuels Complex. In the building shown there, it actually has our name on it now, Aurora Fuel Fabrication. We've been granted access to 5 metric tons of HALEU being produced from processed EBR2 spent fuel. So the lab is taking EBR2, old EBR2 spent fuel, processing it, removing the sodium out of that, and in the process of doing that, creating high-assay low-enriched uranium, which we've been granted access to. So our first reactor is actually going to run off of recycled fuel. And as I said, we've got the building out there. This facility will be DOE authorized because it's within the Idaho National Laboratory. Our reactor will be in our C licensed and a commercially operated facility. Next slide. So let's talk about fuel cycle, what we're looking at. So currently, what you have is uranium ore comes out of the ground, ultimately enriched to 4.95% for the existing fleet, creates depleted uranium in the process, fabricate fuel, run it through the light water reactors, produce electricity. Now it currently goes to interim storage. Ultimately, it would go to deep geologic repository. What we want to do is actually take that fuel from the light water reactors, bring it to a recycling facility that Oklo will own and operate, and recycle it into fuel for our reactors. If you follow the bottom line, it's the same process as basically the light water reactor fuel, except we will be enriching up to 19.75, creating metal fuel, and then create the Oklo fuel. Now, I have to emphasize here that recycling does not eliminate the need for a geologic disposal. There will always be a need for a deep geologic repository. It's just that the materials coming out of the recycling facility will be different than, say, the spent fuel coming directly out of the reactor. But there'll still be high-level waste that needs to go to a deep geologic repository. So we intend to take light water reactor fuel, recycle it, make fuel for ourselves. Then we intend to eventually recycle our own fuel, which you see down on the bottom, and then make fuel for ourselves as well. Next slide. So from our perspective, recycling is important because we own the entire our reactor and the operation. And I said, we build, own, and operate, and we are selling electricity at the end of the day. So we're going to be pursuing a commercial scale recycling facility using technology, electrorefining technology, based on the decades of work at Idaho and Argonne National Laboratories. Oklo has engaged the Nuclear Regulatory Commission. We're in pre-application interactions with them. We have not published a date as to when we'll submit an application to NRC. But from our perspective, recycling is expected to produce fuel more cheaply than fresh HALEU. And again, I mentioned HALEU as an important note here because that is more expensive uranium than going in the light water reactor fleet. So the economics for us on recycling are different than the economics for the light water reactor fleet, plus benefits to the back end. Next and last slide. So this is an image of the Aurora powerhouse in a beautiful location, not Idaho. Not that Idaho's not beautiful, sorry, I didn't mean that. But the image here is of our building as we have designed it. And so we look forward to having folks come and visit when we have a reactor up and operating. With that, I will conclude. Thank you.
Okay, good afternoon, everybody. My name's Paul Murray. I've been with DOE for 1 year. Prior to that, I worked in the commercial nuclear industry for 44 years. originally from England. I've worked on most of the commercial scale reprocessing plants in the world, and also worked on sodium fast reactors. My second job in 1986 was reprocessing fuel from a sodium fast reactor on a commercial scale in the UK. Okay, so next slide, please. So DOE is in negotiations, good faith negotiations with several of the advanced reactor companies to manage their spent nuclear fuel. So nothing I say today should be construed and taken as DOE's position during any contract negotiations that we might be having. Next slide, please. So DOE is currently funding a lot of different advanced reactor designs. As the designers and operators consider the operating costs of these reactors, they have to remember the costs associated with the long-term disposition of spent nuclear fuel. Next slide, please. As was mentioned earlier, we have been using nuclear power in the US now for over 66 years. In 1982, the Nuclear Waste Policy Act was put into place. At that time, DOE signed standard contracts with the light water reactor utilities to basically collect their spent nuclear fuel and manage their spent nuclear fuel for a long time. The utilities started to pay into the nuclear waste fund based on a fee, based on the amount of electricity that they produce. Today, that nuclear waste fund stands at about $50 billion. The important takeaway from this slide is there's a long established program for management of spent nuclear fuel from advanced reactors in the US. And the cost of disposing of a light water reactor assembly is pretty much a wash between the different types of light water reactors that are currently out there. Next slide, please. So currently we have 94 operating reactors, 20 reactors are completely shut down. Today, as we sit here talking, there's 95,000 tons of spent nuclear fuel from the light water reactors. At the end of life of the current light water reactor fleet, there will be 140,000 tons of spent nuclear fuel that need to be managed and disposed of in a deep geological repository. Next slide, please. So my program is also responsible for disposing of defense programs, high-level waste. So DOE Environmental Management is turning high-level waste from the reprocessing of 140,000 tons of spent nuclear fuel into vitrified canisters. These canisters are approximately 2 feet in diameter, 14 feet tall. DOE EM, over the next 30 to 40 years, will produce somewhere between 21,000 and 29,000 vitrified high-level waste canisters as a direct result of reprocessing of, as I said, 140,000 tons of fuel. Next slide, please. So, as previously mentioned, DOE was supposed to start picking up spent nuclear fuel in 1998. In 2014, the utilities sued us for partial breach of contract. We lose, on average, about $800 million a year, which is paid for by the US taxpayer. The number was just amended last week. Last year, the total liability increased to about $3.5 billion. So now, for partial breach of contract, we're close to paying $50 billion to the US utilities. To put that into perspective, $50 billion is about the cost of 4 nuclear-powered aircraft carriers. Okay, so that's how much we're going to pay to the US utilities moving forward. And next slide, please. My program, therefore, is important. We are responsible for turning up to the reactor site and taking title to the spent nuclear fuel at the gate, transporting that spent nuclear fuel to an interim storage facility or to a geological repository program. It's important to remember that the Deep Geological Repository Program, 20% of that cost will be paid for by defense programs. The other 80% will be paid for by the commercial nuclear fleet. Next slide, please. So DOE because we're funding all of these advanced reactors, we set up a working group called a Back-End Management for Advanced Reactors. So DOE has been looking at the storage, transportation, and long-term disposal of advanced reactor fuel. This group started over 2 years ago and is now concluding. We are ready to start negotiating an amended standard contract with these advanced reactor companies. It's important to remember that the original contract that was negotiated with light water reactors during the last nuclear renaissance about 15 years ago, when we were going to build over 25 big PWRs, the standard contract was amended. So any reactor that is built now, including Vogtle 3 and 4, cannot sue DOE for not picking up their spent nuclear fuel. The new contracts say the DOE will collect the spent nuclear fuel at some point, so many years after the reactor has shut down. Okay? Once again, there's nothing technically stopping us picking up this spent nuclear fuel and disposing of it. However, I'm going to keep going. Next slide, please. National Repository. So the Nuclear Waste Policy Act is still the law of the land. There is a waste acceptance criteria associated with that Nuclear Waste Policy Act and the Yucca Mountain site. So we can accept no RCRA material into a future repository. As a previous speaker mentioned, we do have an operational deep geological repository at the Waste Isolation Pilot Plant. Following an incident there that shut down that facility for 2 years, we will take no pyrophoric material into a future deep geological repository. We'll also take no liquids. The design of a repository is in part based on criteria such as heat load. So if your fuel is too hot, it will have to stay at the reactor site and be stored until such time it can be shipped and disposed of. This is also a very important point. Everybody has to pay their fair share of the cost of final disposal of the spent nuclear fuel. Okay? DOE is not responsible for treating spent nuclear fuel or high-level waste to meet the criteria. This has to be part of the O&M cost for the reactor. Okay? For public confidence, spent nuclear fuel that finally makes it into a repository will have to be retrievable for 50 to 150 years after the last waste package is placed. Next slide, please. So in conclusion, we're 50 years into a nuclear waste management program in the US. Spent nuclear fuel management cannot be ignored, and it is an important part of the NRC licensing process for new reactors. The reactor operator, let's start this, NRC licenses the design of the reactor. To get a construction permit to build the reactor operator has to be in good faith negotiations with DOE. We're in good faith negotiations with everybody. To get an operating license, the reactor operator has to sign an amended standard contract with DOE. Okay? Another important fact, DOE is not responsible for the management of coolant. Final disposal, everyone pays their fair share. Reprocessing still results in high-level waste. As I mentioned, EM has reprocessed 140,000 tons of spent nuclear fuel and will produce 21,000 high-level waste canisters. And I'll say this again because some people don't believe this. To obtain an operating license from NRC for your reactor, the new reactor operators has to sign an amended standard contract with DOE to accept the spent nuclear fuel for long-term disposal. And that's the end of my presentation.
Wow, thank you very much. That was not just informative, it was also really interesting. Even I learned a couple things there. Thank you, Matt and Everett and Paul, for sharing such an insightful presentation. With that solid background on the report and some of the broader issues related to waste disposal, we're ready for our live Q&A. And as a reminder, you have 2 options for asking a question today. You can type your question along with your name and your affiliation in the Q&A box, and I will read it out loud. Or you can use the raise hand feature to let me know that you'd like to ask a question live, and that way I will call on you. So all of our speakers I see here are back on camera and mic, which is great. I don't see any questions in the Q&A box. Fortunately, I've gotten some in email, so I'm going to start there. Matt, you talked a little bit about Finland and some other countries. I'm wondering if you want to elaborate any on what other countries are doing or planning to manage their spent nuclear fuel. And then Everett or Paul, if you want to add anything to that in terms of having some perspective of other countries versus the US.
Yeah, sure. And I bet Paul would be even more up to date than me. I mentioned some of the countries that to me look like they're making good progress. And obviously Finland is sort of within that range of starting disposal operations, which would be a world's first for disposing of commercial spent nuclear fuel. I mentioned we do have this operating repository in New Mexico, but it is just for defense waste and just for transuranic waste. It's not spent nuclear fuel per se. Sweden's not too far behind Finland. They're similar programs. The news was either last week or maybe even this week, that Canada had finally down selected to their one site, which had been an ongoing process. They've had this voluntary process where local communities have been free to withdraw themselves at any time, and those communities have stayed with it. And both of the final two, the local governments had voted in favor of hosting the repository. So I think that's an interesting example to look at. But Paul would probably know better the sort of broader international landscape.
So I can tell you, so several aspects to this. One takeaway from this is the US is the largest user of nuclear power in the world, right? We're the only Western country, with the exception of Spain and the Ukraine, that does not have a deep geological repository program. Right? We talk about tripling nuclear, but we don't have a deep geological repository program. So what are we doing? So there's the countries that do have a repository program, there's a group called EDRAM, EDRAM, and we meet twice a year to exchange on how everybody's doing. It's a small meeting. Last year it was in Japan, and this year it's in Japan. Next year it's going to be in Germany. The US actually set that group up and led that group to begin with, because we were the world leaders at one point when Yucca Mountain was there. So we do meet regularly with these other countries to get their lessons learned. Specifically related to advanced reactor fuels, we have and are negotiating agreements with the UK, who had sodium reactors and high temperature gas reactors, Japan, Germany, and Belgium. So government to government relations. So we share information. On the world stage, the US is actually leading a study for all the repository countries, looking at how to dispose of spent nuclear fuel from advanced reactors. Okay.
Thank you. Eric, I think you wanted to add something.
Yeah, if I could just add here, I think the announcement that Matt talked about earlier that Canada made is a really big deal. Canada's Nuclear Waste Management Organization announced, it was last week, that they selected a site in northern or western Ontario for where they want to construct that permanent repository. And this is really the culmination of, I think, a roughly 14-year site selection process. And looking ahead, they plan to start constructing sometime in the 2030s. So that's really exciting news. And much of that success was predicated off of the engagement they did with the two communities that reside near that site, which is something, we in the United States can look towards as a great example of how sort of a more consent-based siting process that I know Paul knows a lot about can really be effective moving forward.
Thanks, Eric. Going to go to questions in the Q&A box. First one is from Philip Chafee from Energy Intelligence. How do the report conclusions differ from the conclusions of the National Academies of Sciences in their November 2022 report on advanced nuclear fuel cycle and waste? Eric, we'll start with you on that one.
Yeah, wonderful question, because a lot of the information provided in this report is based off of that National Academies of Science report. When that came out, I think it was a couple hundred pages, and reading through it and talking to folks, I it was hard to meet someone that actually read all of it, right? So part of the job that we sent out to do, me and Zach Koshgarian, analyst at NIA, who also contributed to the report, was to delve through that National Academy's report, pick out sort of the key information so we can really distill it for policymakers looking forward. We also noticed one of the things that wasn't really focused on in that report that we decided to focus on was the interim storage capabilities that we have. I talked a lot about what we're going to do to store and manage spent nuclear fuel from reactors in that interim time period in the near term and midterm before we get to that long-term permanent disposal pathway. And I think that really contextualizes sort of what we're looking at doing and how well set up we are to handle a lot of these advanced reactor waste in the near and midterm.
Great, thank you. A follow-up question from Philip for Paul, and I know Paul's going to have to leave in a few moments, so we're going to go to Paul on this one. What's the outlook for a consent-based siting process for a permanent repository in the U.S.?
A great question. So first of all, there's no engineering or technical barriers to stopping my program moving forward with a deep geological repository program. Nothing at all. It's just political will to let us go and do it. Okay. So when Congress says go and do it, then we will be ready to go, basically. We are right now, during this year, we're 2 years into a consent-based siting process for consolidated interim storage. We are doing lessons learned from that process to basically be ready to start a process. Consent, collaborative, cooperative, it's all in, that's what we need to really move this forward. But we're getting ready, lessons learned, to be ready to start when we are authorized by Congress to do so. Okay.
Got it. Thanks. Anyone want to add to that before I move on to another question? Okay, a question from Alexis Weiss of Bloomberg Law. Thank you for taking the time to go over policy around nuclear waste storage. It's very helpful for energy reporters like myself who are following developments in nuclear plant regulation. Are there backup plans in place in case nuclear plants or high-level waste locations run out of room to store spent fuel on site? Who wants to go first?
So let me answer that question. So this is a long-term problem. If you look in the US, 20 reactors are shut down and being decommissioned. Some of those reactors, the reactors being decommissioned years ago. I went up to visit the three Yankee plants recently. Main Yankee, all that's left on an 820-acre site is for spent nuclear fuel. Okay, so there's always plenty of room for expanding your interim storage, on-site interim storage to accommodate more spent nuclear fuel. So hopefully the current plan, subject to appropriations, is to have the government-owned consolidated interim storage facility open in 2038. At that point, we start moving 3,000 tons a year of fuel from the sites to the first of the consolidated interim storage facilities. So we shouldn't run out of space at the reactor site. Does that make sense?
Yes, thank you. Anyone else want to add to Paul's background?
This is Everett. What I would add is, I mean, as the industry progressed, we stored fuel in spent fuel pools, water-cooled pools. And as those filled up, we moved into and developed dry cask storage systems. And as Paul said, there's plenty of room at the existing reactors, operating reactors, to continue to do dry cask storage there. And companies like ours are planning for storage of fuel as well at our reactor sites. And then for us, eventually, we'll move it to our recycling facility.
Great, thank you. One more question from Ruben Baylor from NIH. How difficult, desirable, or potable would it be to find another country willing to just buy our SNF?
That's a good question. I get this question all the time. We can't just give it away. We can't. We generated it. You know, nobody's going to take anybody else's spent nuclear fuel. Even when so I worked at most of the major commercial reprocessing plants, or was involved with the companies, even the big reprocessing companies that reprocessed fuel commercially, returned the high level waste back to the country of origin. Okay, so you got your plutonium back, but you also got all the waste products back as well. Okay, so it's going to be it's almost impossible, I'd say, to find a country that would take, in the Western world, let me qualify that, in the Western world, it'd be very difficult to find a country to take your spent nuclear fuel and dispose of it.
Thank you, Paul. Anyone else?
Yeah, I'll just add a little bit on the sort of yes, we can theme. We can do this. We know that what it takes to store the spent fuel on an interim basis, it's, you know, has some different characteristics for the advanced reactor waste than for the conventional waste, but we know how to do this. We can store it safely. We can store it safely for many years. We can store it safely for many years as long as it takes us to set up a repository. But we really do need to set up a permanent repository, and we can do this. Other countries have done it. This is actually something we can do. We know how to do it technically. We also know how to do it from a process point of view. We need to do consent-based siting because we have to put it in some place where the communities will accept it. There's really, you know, in our form of government, there's really no alternative to making sure that you have buy-in from the communities surrounding where you're going to put the waste. So we can do this. It's really important that we do it, and it can take some time. We do have some time because we have the interim storage capability, but it is something we need to pursue, and it's not something that we have to wait for other countries to do for us. We can do this.
Thank you,
Can I
Judy.
just say one thing? Can I just say one thing? That's part of the problem. Spent nuclear fuel is safe in storage. It's boringly safe in storage. Nothing's happening to it. So that's our problem. It's boring, it's safe, but at the end of the day, we have to do something with it. Okay? I'm so sorry I have to drop off.
We understand.
If there's any
Go for
additional
it.
questions, please.
We'll share the last one with you by email.
Thank you.
Thanks so much for joining us, Paul. This question is for Oklo. So Everett, how do you think about SNF planning for microreactors in remote locations? Do you envision SNF being stored on site in dry storage for a period of time, or do you envision shifting SNF rapidly to centralized interim locations, perhaps at the recycling facility? And this is from Philip Chafee at Energy Intelligence.
Thank you. Thank you for the question. So I would say first that we're designing like I said, a 15 megawatt electric reactor and then moving to 50 megawatt electric. So our target market is not necessarily remote locations. Certainly if that is an opportunity there, then we would do that. But for the most part, remote locations are not the primary target location. But with that said, our intent is to manage spent fuel on site until such time as it is ready to be shipped to our recycling facility. We would not be utilizing any other facility unless, of course, the federal government, as Paul was talking about, opens up some sort of centralized interim storage facility that companies could access. But we're not planning on that. We're planning on managing the spent fuel ourselves at our site and then shipping it to our recycling facility at the time that's appropriate.
Great, thank you. We have a question from Kurt Harris. I'm not sure if Kurt's affiliation, he didn't include it. It was really for Paul, but perhaps others of you might want to chime in a bit here. Are any advanced recycling techniques being supported by DOE and e.g. to make needed fuels for advanced reactors? We talked about this a little bit in the presentations, but anyone want to address at least part of that?
So what I would throw out, say there is, Oklo's taken advantage of a number of awards and opportunities through ARPA-E. Within the Office of Nuclear Energy, there was in FY24, $10 million put in, appropriated for a cost share program to support R&D for recycling. The department has not issued that funding opportunity announcement yet, and in FY25 appropriations, which has not been resolved yet. We're in a continuing resolution. There's two different approaches. The House is putting more money into the same program, and the Senate is trying to establish a second program. So there is support for recycling at the congressional level. There's support and money being provided to the Office of Nuclear Energy, but we have not seen the funding opportunity announcements come out yet. We're looking forward to it.
Thank you for that. That was really helpful, and you will get the last word, Everett. So 1 hour is done. Hard to believe. It's actually not enough to fully address a topic as complex as this, but I hope we gave everyone at least a solid start to some ongoing conversations. If you are a member of the media and you want to talk with NIA in more detail, just let me know and I will follow up with you. For now, please join me in thanking each of our speakers for joining us today, Matt Bowen, Everett Redmond, and Paul Murray. On behalf of Judy, Eric, and the entire NIA team, thanks for joining us today, and we look forward to seeing you again online for our next briefing. In the meantime, happy holidays to you and yours, and thank you for being with us today.
Thank you.
Yep, thank you.